You probably learned it in grade school, parallel lines never meet.
They stretch on to infinity, always maintaining exactly the same distance apart. In our everyday world, on a piece of paper, on a flat table, this seems obviously true.
It is the very definition of parallel. But here is the thing, that is only true in one very special kind of geometry. Flat, Euclidean geometry.
The geometry most of us learn in school.
What if the space itself is curved? What if the rules change when the surface bends?
That is the question that led to one of the most profound revolutions in mathematics.
This is Euclid's fifth postulate, the parallel postulate.
It says, through a point not on a given line, there is exactly one line parallel to the given line.
Simple enough. But for over 2,000 years, mathematicians found this postulate deeply awkward. It felt less elegant than Euclid's first four postulates, more like a theorem that should be provable from the others. Many great mathematicians tried to prove it. All of them failed. When mathematicians finally tried assuming the opposite, that the fifth postulate was false, they discovered something remarkable. Not a contradiction, but entirely new, self-consistent geometries.
Geometries where parallel lines can meet, and geometries where they can diverge apart.
The age of non-Euclidean geometry had begun.
Let's start with the sphere, the most intuitive example of curved space. On a sphere, the shortest path between 2 points is not a straight line in the usual sense. It is a great circle, like the equator or a line of longitude.
These are called geodesics, the closest thing to straight lines on a curved surface.
Now here is where it gets fascinating, any two great circles always intersect. On Earth, the lines of longitude are all perpendicular to the equator, and they all converge at the north and south poles.
This means on a sphere, there are no parallel lines at all. Period. Every line eventually meets every other line. And triangles?
On a sphere, they behave completely differently. A triangle's angles add up to more than 180 degrees.
The larger the triangle, the greater the excess.
Draw a triangle from the equator to the North Pole and back, and each angle can be 90 degrees, that is 270 degrees total. This curvature is measured by the Gaussian curvature, k, which equals 1 over r squared for a sphere.
The larger the sphere, the smaller the curvature.
This is called elliptic geometry, a space with constant positive curvature.
Now imagine the opposite, a saddle-shaped surface. This is hyperbolic geometry.
On a saddle, the surface curves in two different directions at once, curving up in one direction and down in the other.
This negative curvature changes everything about geometry.
Through a single point not on a given line, you can draw infinitely many distinct lines that never intersect the original line.
In the Poincaré disk model, the entire infinite hyperbolic plane fits inside a circle.
The straight lines become arcs of circles that meet the boundary at right angles. And the triangles here, they have angles that sum to less than 180 degrees. The larger the triangle, the greater the deficit, and the deficit is directly proportional to the area. The Gaussian curvature here is negative, k equals -1 over r squared. For nearly a century after its discovery by Gauss, Bolyai, and Lobachevsky, hyperbolic geometry was viewed as a mathematical curiosity. A consistent system, yes, but surely just an abstraction with no connection to the real world.
Then came Einstein. Einstein's general relativity revolutionized our understanding of geometry forever.
It showed that mass and energy do not just exist in space, they actively curve spacetime itself.
The geometry of our universe is not just a mathematical abstraction.
It is a physical, measurable property of reality.
So which geometry describes our actual universe?
In a flat universe, parallel lines behave exactly as Euclid described, they stay parallel forever. In a closed universe, one with positive curvature, parallel lines eventually converge and meet, just like on a sphere. In an open universe with negative curvature, they diverge away from each other.
Measurements from the Planck satellite show our universe is nearly flat to extraordinary precision, but the question of its exact global shape is still one of the biggest open questions in all of cosmology. Euclidean, elliptic, hyperbolic, three geometries, three different answers to what happens to parallel lines.
And the question of which one truly describes our universe is one of the deepest in all of science. Is the universe flat, closed, or open? We are still trying to find out. Because geometry is not just about shapes on paper. Geometry is the very fabric of reality.